Now, in doing so, we find that the theory and concepts of this topic are based upon what we call the kinetic molecular theory. Now, the kinetic molecular theory is typically introduced to the student in these courses in gas laws and relate specifically to the gas phase behavior. However, the kinetic molecular theory is not just limited to gas phase behavior, it's also limited to solids, liquids, and even plasmas if you want to get into that issue. The postulates of the kinetic molecular theory relate to the behavior of a molecular level character of whatever substance it is in your that you're studying. So, kinetic molecular theory describes molecular level character of matter. And is broken down into 5 fundamental postulates that describe the behavior of particulate matter. The first one is all matter is composed of particles, elements, atoms, molecules, and compounds. I think that's kind of self-evident in the growth in your history of studying the material world. I think we all believe in atoms at this point in our education. Particles interact by attractive and repulsive forces and relate to what is known as the inverse square law. Particle-particle interaction Okay, for solids, the force is large attractive forces well, I better write it down. And gases gas particle interactions are considered to not exist of extreme distances between you may see postulates of the kinetic molecular theory only specify the gas phase interaction when it is generally assumed that the interactions are zero in terms of attractive and repulsive forces because of the distances in movement, as well as the what we call the excluded volume of the particle is non-existent. So they are there, but they're not there. So it's a kind of a conundrum in terms of defining the interactions as an attractive or repulsive. But as you change from solid to liquid to gas, of course, the force of interaction decreases, which allows the particles to remain apart. I think you learned that in Chem 1. And these are divided into 3 modes of motion. Translation, rotation, and vibration. Translation, as you would expect, is movement from point to point in a straight line. Rotation and vibration are self-defining. The velocity and also the speed of particles is directly proportional to its kinetic energy content. If you heat a material object, the particle's motion begins to increase, and that is translated in because it has higher kinetic energy. The particles move faster. You can generally say velocity is proportional to kinetic energy, and kinetic energy is proportional to heat content, which is proportional to temperature. Which makes sense if you stop and think about it. When defining the velocity from an empirical standpoint, we find that in gas phase systems, the velocity is called the RMS velocity. Is root, and I'll explain this when I get into the collision state theory. Root means square speed. And another way is just the average speed of all the particles in a given container. And it's given as, well, actually, the square root of 3RT over M, which is the mole weight. Number average, what they call the mole weight. Well, I've normalized this into meters per second, and it translates to 158 OT over M, mole weight, and that's your your Kelvin temperature. So if you wanted to get the RMS velocity of oxygen at 25 degrees C, which is 298 Kelvin, oxygen has a formula weight, Mn, 1632. So the RMS velocity for O2 is 158 onto the square root of 298. Oh, don't worry about the unit. I've taken care of that in this coefficient here. It's constant. 198 over 32. And just tag it with meters per second. It's a real simple calculation and formula. Deriving is not quite as simple, but I've tried to present a very simple, quick way to calculate these particle velocities. Especially gas phase. Is considered to be perfectly elastic. That is, the sum of all your changes in energy equal zero. There's no net energy change. In reality, when particles interact by collision, there is a heat loss. And to regain the energy, it absorbs electromagnetic radiation. But the amount lost in collision equals the amount of energy gained from electromagnetic radiation, so they cancel each other out. So the scientific community, in writing these postulates, just simply says, well, they're running into one another, but the net effect is zero energy change. And that's what we call a perfectly elastic collision. Zero energy change as a result of the collision. P, A, M, and I just have to remember VC. Particles, attraction, repulsion, movement, velocity, and collisions. So that just kind of gives you a little list that will help you initiate more information on the subject that as you need it. One of them is the collision theory. And the other one is a transition state, which we'll talk about in a few minutes once we finish this. It says that for a set of reactants to produce products, 4 events must occur simultaneously. Don't get this mixed up with the rate factors. But these I call reaction factors. And spell the word C-E-N-T. So don't get it mixed up with can't see. Can't see was the set of rate factors. You change one of those in the can't see list, you change the rate of reaction. Concentration, area, nature, temperature, and concentrations, or catalyst. Here, C still stands for concentration, but what it means is an effective kinetic concentration. So if you have a reaction A plus B going to, say, AB, then you would put a lot of A particles and a lot of B particles in the container, and they'll run into each other and react, right? I mean, that's logical. Okay, however, what I mean by effective concentration, A and B must be able to find one another. That means if I had in this room that we're looking at, a particle of A in the back room of the room and a particle of B in the front of the room, they have a hard time finding one another. That's an ineffective reactive concentration. So what do? We just fill up as much as we can in one or the other, or make them where they can find one another. And it's frequent to overload one of the components relative to the other. Once the other, it would be called the limiting reagent, goes away, reaction stops. But you know that all of it's been used, and you can calculate how much of the other one has been used based on chemical equations. So one of the first things in the idea of the collision theory is that you must have an effective concentration. The molecules got to find one another. They must have effective collisions. This is an orientation factor. In that, if you consider for a moment, my hands are molecules fixing to react. And so if I bring them together wrist to wrist, they don't interlock. But if I bring them fingers to fingers, they interlock. So there's a very specific orientation. Molecules have a three-dimensional nature. And so that three-dimensional nature is very important in orienting with the other. A and B must be oriented in a certain way in order to react. In the probability of forming a product, if you have a high number of collisions, the probability of effective collisions increases. It's just a lot of them bouncing into one another. And the higher the number of collisions per unit time, the greater the probability of forming a product. N stands for naturally reacting substances. You must have in the container, A and B must be naturally reacting substances. In a way, this is self-explanatory in that nature has its own set of compounds that reacts with another set of compounds in nature. And if you put in the wrong compounds together, if you put two salts, cations together in a solution of sodium and potassium, you're not going to get any reaction. Or chlorine and bromine, there's not going to be a reaction. However, if you put sodium ions with chloride ions, you will get an interaction. And of course, giving an ionic sodium chloride. And T is temperature. for activation. Now, temperature fit my acronym, that's why I use it, but it's actually, you must have the proper activation energy applied to the reactants. Ineffective is what they say. And activation energy is a very important term that we will see as we expand this concept. But these four events, proper kinetic concentration, effective collisions, orientation, they must be naturally reactive, and you must be at or above an activation energy for the system undergoing reaction in order to produce product. These four events are probability factors in forming and increasing the formation of the products. Okay, this diagram is referred to as a Maxwell-Boltzmann distribution curve. And it refers to the distribution of particle energies or particle velocities, they're in general the same here, for all the particles in a given container. Now, I think it's easy to visualize that if you consider mentally all of the particles in this room, you can honestly say that they do not all have the same energy content. Some of them have high energies and some of them have lower energies. And plotting the energy distributions and the mechanics of that is beyond the scope of what we're doing. What you generate, though, is in our scope, looks like this. And this is at a given temperature, say temp 1. So, for example, room temperature, well, we're about 25 degrees in here, so that's the standard average. At any rate, at temperature 1, we could say we have some low energy particles or low velocity particles, and then the majority in the room will fall within this portion of the curve, and then there are a rare few that are in the high end velocity of this curve. Now, considering this being the mass of particles, or the total number of particles, see over here on your y-axis, what you want to do is you want to heat these particles so that you increase the probability of the four events occurring quickly or more efficiently. And the idea is to push the particles past this vertical line. And it's an energy point. That energy point is the activation energy. And it is the point at or above which the four events occur simultaneously. Listen to this. If the particles are not at or above that, no reaction occurs. It has to be at or above the activation energy. Now, the idea is to increase the number of particles that do have the opportunity to cross those, have those four events occur. So if you increase temperature, what's going to happen? Well, some of these particles will shift to the right, and you'll see the curve transition into that diagram. And that'll be T2. Of course, T2 is higher than T1. It's heating the gas particles. And there are more particles with higher energies and colliding more and increasing the probability of generating the proper orientations and on, and we get products. And you continue to heat those, and the number of particles continues to increase to the right, T3, and you can actually eventually get them to all of them above that activation energy, and this is not drawn to scale, obviously. And an increasing temperature increases the probability of the reaction to take place, and this is one of the foundation justifications for, okay, go heat your reactants and make them into products. That's why we cook food, so that we can get it to the reactive end. At any rate, this is what we call the collision theory of particles. It depends on the particles achieving those 4 reactive events at and above the activation energy. That's the collision theory. I'll say it again. The collision theory of reactivity is the process of making the particles in a reaction achieve 4 simultaneous events. That's what you're trying to do in any reaction. Those are the CENT issues that we just talked about. And all of those are occurring at or above the activation energy. So that's theory number 1. Now there's a lot of math that goes into this, and if you stay with chemistry, you could probably develop the probability equations that define these curves. And you typically, you'll see them in the junior level physical chemistry type courses. And this will lead us to a very specific type of problem that is called the Arrhenius equation problem, and I'll show you that when we finish this. Now, in the transition state theory, it is a diagram that defines the behavior of a reaction in progress. And it's easier to draw these. Now, there are 2 diagrams you need to be aware of. One is for endothermic reactions, and one of them is for exothermic reactions. So, we'll start with the exothermic reactions. And these are potential energy diagrams. And essentially is an energy axis vertically like this, and reaction progress axis along the x-axis. I call it positional energy. It seems to have a better connotation. Most people understand potential energy is that stored energy. I place this marker pen on the stage of my marker. It has a certain amount of energy relative to the floor. If I push it off, it loses that energy and hits the floor. Well, so do particles in a reactive process, and we'll learn more specifically about that when we get to thermodynamics. Well, you have particle energies of the reactants and particle energies of the products, and they are classified as a potential energy or energy content. So if we start, say, right here with the potential energy of the reactants, I'm going to say E of the reactants. So we'll call that the potential energy or positional energy of the reactants. In order for that to, well, let's see, a better way to say this is after the reaction's taken place, we'll have the positional energy of the products. which will be down here somewhere. And put the notation over here. And so that's the energy of the products. That's where it will be on your energy line. Now, to go from the reactant energy to the product energy over here, we have to go through the activation energy, because the reactants are not going to react until you push it to the activation energy. And in doing so, you'll find that you will have to heat the sample to that activation energy. And when it crosses that activation energy point, it will then fall over the hill and then go to the energy level of the products, which is below the level of the reactants that you started. But this point right here is the EA, and the change of energy is what people use to define what we call the delta E activation of the forward reaction. Activation energy, FWD, is the amount of energy you need to put into the reactants to push them to the activation energy, where they will experience those 4 events. Once they go through the 4 events, then they produce products. If you wish to push the reaction back in reverse, you would have to push energy back into the the products, to break them apart and push them back over the hill. And that's called the activation of energy for the reverse reaction. Right there. Now, there's one more energy in here, which is the change in energy of the reaction, which is the energy content of the products minus the energy content of the reactants, and that gives you your net energy change, and that's delta E of the reaction. If that delta E of reaction is if the products are below the reactants' positional energies, will come out less than 0, and that's what defines the exothermic reaction. So this is your defining item in that diagram, and I got some problems we'll work with this. They're very simple. As soon as I finish the next one, then we'll take a break, come back and do the Arrhenius equation, and I'll do the background stuff on the experiment. When you have to deal with an exothermic reaction, you will start at some point in the energy line on the energy curve, go up to the activation energy, and will finish below the energy level of the reactants. That's an exothermic diagram. An endothermic diagram will end up above that initial energy content. Okay, so as indicated a moment ago, the potential energy diagram for an endothermic will end up above your starting point. So this would be the energy content, potential energy, positional energy, whatever, of the reactants, whereas this would be the potential energy content of the products after the reaction is completed. And in this case, when you identify the forward and reverse activation energies, they will start, of course, with the energy content of the reactant. You'll go up to the activation energy point up here, and then the difference in those two will be the forward reaction, like that. Now, and the the activation energy point, it will be up here, and then you will have two energies over here on the right side of what I call a center line, if you will, kind of a center line of the curve. But at any rate, if you want to look at the activation energy of the reverse reaction, it would be this amount of energy, and then the differential between the products minus the reactants would give you an energy value or reactive energy value greater than 0. So this would be the reaction energy greater than 0, and that defines the endothermic reaction right here. Okay, so you're looking at these potential energy diagrams in your worksheet that I handed out some time ago, a couple classes ago, I guess. If you look on that last page, you should find this problem. It says sketch a potential energy diagram for the reaction. The activation energy for the forward reaction is 10 kilojoules, and delta H of the reaction itself is a minus 200 kilojoules. What's the activation energy for the reverse reaction? And label your diagram appropriately. So when you look at this and you see something like that, that's a negative value. What does that tell you? Is it endothermic or exothermic? Exothermic, right. So you want to draw an exothermic reaction diagram. So you get in. It doesn't matter scale-wise. This will be the reaction progress, potential energy, and if it's an exothermic reaction, it'll follow a trend like this, where the products will wind up at a point below the reactants. And here is your activation point. Activation potential energy be up here. So when you look at this, this would be the energy of the forward reaction, and the reverse reaction would be over here. Right there, and this will be your energy of the reaction. You can split this in half using, say, a little guideline like that. And you can see the sum of these two always equals the reverse reaction in the exothermic. When you go to the endothermic, you'll see this sum of two energies over here on the right equaling the activation energy of the forward reaction in the endothermic. So it's given that the activation energy for the forward reaction is 10 kilojoules. And the reaction is a minus 200 kilojoules. That's the differential between the starting point and your energy point down here. But what they're asking you for is this reverse reaction. And if you look at the distance between the two, you have to add those two together. That's just a number that says the differential is a negative number, that it gave off energy. But that doesn't say subtract 10 from 200 or use 200 minus 200 plus 10. So to get this reverse reaction and how much energy you need to push the products back over to the reactant side, this would equal 10 plus 200 kilojoules. is a distance factor. That's how you work these diagrams, problems that you're going to see come test day. So if you'll split it down the middle, you can see who adds to give you what. Okay, here is sketch the potential energy diagram for decomp of dinitrogen monoxide. And the activation energy for the forward reaction is 251 kilojoules. And the delta H, or the energy of the reaction, is 176 kilojoules. Notice it's positive. So that says it's an endothermic reaction, and so you want to draw an endothermic diagram and then put the values into that. Okay, so it says here the forward reaction is 176 kilojoules to activate, let's see, the activation energy is 251. Sorry. Here to here. And you see the reaction is 176 kilojoules. That's your delta E for the reaction. It's also delta H, which we'll cover when we get to thermo. So the reverse reaction will be this one right here. Well, that's a difference between these, 251 minus 176 kilojoules. And that's 75 kilojoules for the reverse reaction. So you see the difference in the two. It doesn't get any more complicated than that. But you must know how to draw the endothermic and the exothermic reactions and where to put in the numbers and make the interpretation of the numbers.